moderator, and it's my pleasure to introduce Britt, who's speaking to you about brook trout population and habitat in the Black Creek watershed. And I'll say, if anybody has trouble hearing in the back there, give me a signal. I can play with the microphone. So, all right, take it away.
Thanks, Fred. Thank you all for coming. My name is Britt. I'm a fisheries biologist out of Region 9 in Allegheny. And today I'm going to be presenting my thesis results of brook trout population and habitat characteristics in the Black Creek watershed. I'm currently in the writing phase right now, and hopefully on a defense date around August of this year, so fingers crossed. So before I get into my product details, I first just want to go over a brief overview of eastern brook trout in the United States. Their range extends from the northeastern portion of Georgia, follows the Appalachian mountain range, all the way up into northern Maine. And within this range, they've really been restricted to small streams that are high in elevation, have cold water temperatures, and have suitable water chemistry, such as high dissolved oxygen. Within these small stream systems, they typically live to be about 4 years old, and this is primarily due to decreased winter food availability, intra-species competition, so competition between older brook trout and younger brook trout, weather events such as high flows and drought conditions, and also spawning mortality. Brook trout spawn in mid to late fall, and during this time they use up a lot of their lipid reserves, and these lipid reserves are really important to overwintering success. So without the lipid reserves, we see a lot of decreases in brook trout populations due to the loss of those lipid reserves, especially in spawning brook trout. So within this range, we've seen population decreases, which has led to extirpated regions and also a loss of genetic diversity. And this comes from a variety of different factors, such as the loss of the riparian canopy and the loss of the riparian zones due to improper land use practices, and also the invasion of invasive pests such as hemlock woolly adelgid and emerald ash borer. Without the riparian zone, we see a lot more stream sedimentation, so a lot more fine sediments entering the stream because that stream bank is eroding much more quickly. So this causes fine sediments into the stream, which reduces forage success for brook trout, and also reduces potential suitable spawning ground for brook trout. We also see decreased aquatic connectivity, so improperly installed barriers such as culverts and dams can separate the downstream portion of the stream from the upstream, causing decreased aquatic connectivity. And then you also have the introduction of non-native species into these systems, such as brown trout and rainbow trout, which can outcompete brook trout in many of these streams. This figure here, or this map on your right, shows a much more in-depth look at brook trout populations. You can see a lot of red and gray. The red indicates populations that have been reduced by 50% or more, and the gray indicates extirpated regions. We see a lot of blue and a lot of green up in Maine and New Hampshire, some of the Adirondack areas, which indicate populations that are relatively stable in strongholds. If we look specifically in western New York, where Genesee County is, we see pretty much only red and gray. And Genesee County is found in an area specifically of just gray, so an extirpated region. However, in 2021, brook trout were reported in a small stream near Black Creek in Genesee County. This is about 40 miles west of Rochester. And the discovery of this previously undetected population, again in an area where we thought that brook trout were extirpated, highlights the importance of evaluating not only the stream that they were found in, but also other streams within the Black Creek watershed for potential other brook trout populations. This is going to leave me my study objectives. So I primarily wanted to learn about other areas, other streams where brook trout are potentially found in the Black Creek watershed. So I looked at different streams and compared their habitats. So I looked at in-stream habitats, so amount of pools, different types of woody debris, and also I looked at the riparian habitats. And I also want to look at the population densities of brook trout, the population dynamics, and also the health of the brook trout. So again, primarily looking at brook trout density, so the number of fish per meter squared, the length frequency histograms, which can give me a good idea of what the potential age structure is at different lengths. And also I looked at length-weight relationships, which can give me an idea of what the health is of these brook trout. And I also used Fulton's condition factor on a scale of 1 to give me an idea of how healthy these brook trout populations are where they're found. So I selected 6 streams within the Black Creek watershed to study. 5 of them were all located in northeastern Genesee County. And then we had 1 stream that was located in southern Genesee County near the headwaters of Black Creek. And these streams were all selected based on their potential to sustain brook trout in some manner. whether they were headwater streams, spring-fed streams, or streams that could provide aquatic connectivity for brook trout throughout the greater Black Creek watershed. One of those streams in northeastern Genesee County was in fact where brook trout were first reported in 2021. Once the streams were selected, we conducted riparian tree assessments along each stream. And these riparian habitats essentially allowed us to determine habitat changes along these streams. And this allowed me to classify different habitat types. So we classified 4 different habitat types along these streams. We had floodplain wetland, primarily comprised of not a lot of trees, but more herbaceous vegetation. We had mixed coniferous zones, mixed coniferous habitats, which primarily were eastern hemlocks, northern white cedars, and white pines. Mixed deciduous habitats, which were primarily oaks, maples, also some beech species, and also emergent marsh, which primarily were not a lot of trees again. If there were, it's primarily eastern hemlocks, but mostly reed species such as cattails, invasive cattails, and phragmites. Once we had our habitats established, we established transects in each of these habitats. Transects were 50 to 100 meters in length, and only the transects were found in only one habitat type. So this immediately allowed us to have our transects in one different type of habitat, which allowed us to easily classify these transects. And I used a cluster analysis by using tree species. So this is a cluster analysis. We have our streams on the left here, and then these are all the transects. And essentially what this did is allowed me to see how these transects were grouping together based on how similar the tree species were. So this not only allowed me to see how the transects were grouping, but also allowed me to basically confirm that what we were calling a mixed deciduous forest or mixed coniferous forest was indeed a mixed coniferous forest based on how the transects were grouping together. So there's a lot going on here, but I really just want to focus on this one large group here. This one group primarily is grouping streams 1 and 2 together. So primarily all of our transects that we classified as being within a mixed coniferous zone. So without really giving too much away right now, streams 1 and 2 all group together. And this could potentially indicate an importance of riparian vegetation, particularly tree species, on potential brook trout densities. So to get into my brook trout surveys, we conducted single pass density surveys in each stream, and we had block nets set up at the downstream and upstream of each transect, following similar methods to Sweek et al. To basically assume a closed population for each transect. This allowed us to calculate the number of brook trout per area. So the area was the length of the transect multiplied by the average width, which gave us the number of brook trout per meter squared. We had a minimum of 3 people for these surveys, typically 1 wander and 2 netters. One of the netters was also carrying a bucket with the aeration unit for brook trout in between the transects. And then once we were done with the transect, rather than besides just calculating the number of brook trout collected, we also took the total length in millimeters of each brook trout, and also the weight or mass in grams of each brook trout. And then within each of these transects, we also calculated different habitat measurements to basically further classify these transects rather than just by the riparian zone. So we looked at water chemistry using a YSI. We were looking at dissolved oxygen, specific conductivity, pH, and water temperature. We also looked at the substrate. So we had a 1 meter squared quadrat that we laid it in the transect, and we had we estimated the percent cover of each substrate type. And then we had rapid habitat assessments. These are essentially a quick way to score different features along the stream based on scales of either 0 to 10 or 0 to 20, depending on the habitat type. And we used a modified version of the glide pool, sustain our Great Lakes brook trout monitoring protocol. And some of the habitats we were looking at very quickly were just the pool variability, the substrate type, like the epifaunal substrate, the stability of the left and right bank, channel flow. So basically just quick habitat features you can look at quickly and observe. And then again, this just really allowed us to further characterize these transects rather than just by the riparian zone. So once I collected all of my habitats, I wanted to basically find a way to determine what habitats were impacting brook trout density. So a good way to do this is running a principal components analysis. And the principal component analysis is essentially a data reduction tool. It's a statistical analysis that basically takes all of your habitat variables, in my case my habitat variables, and reduces them into your principal components, which are essentially ways that the PCs, the principal components, retain the variables that explain the most variance in your data set. And these principal components are essentially the variables that are impacting the factor. And in this case, the factor is my brook trout density. So how are these habitat variables impacting brook trout density? My max brook trout density was 0.26 fish per meter squared, which is quite a bit based on other studies that I've read. And the principal component here, you can see that the yellow dots indicate high brook trout density in transects. So each dot is a transect. All the red dots indicate transects that had 0 brook trout found, so 0 density. And then all the other colors are varying levels of density found within the transects. So we have our dark purple and blue as indicating low brook trout density, and then our lighter greens and our yellows indicating high brook trout density. So PC1, principal component 1, explained the most variance within this data set. And principal component 1 was primarily explained by cobble, gravel and pebble, and also specific connectivity. If we look to the right side of this PCA here, we can see that low specific connectivity, transects with low specific connectivity, a lot of cobble and a lot of gravel had all the transects where no brook trout were found. It's not until we get to transects that had high specific connectivity where we start to see all of our transects starting to come into play here. So high specific connectivity could potentially indicate, in this case, streams that are all spring fed. So you have a lot more minerals coming in from the ground, which can cause higher connectivities. PC2 further explains the rest of this data set, primarily by the substrate type. So streams where we had a high specific connectivity and a lot of silt, we started to see more transects with brook trout. Again, we got a dot up here. So we have our high specific connectivity and silt pointing in that direction of that highest transect there. But we're still seeing a lot of red. So we're still seeing a lot of transects without brook trout. It's not until we get to streams with high specific connectivity and also a lot of woody debris and sand, so that coarser substrate, we're starting to see a lot more density of brook trout, as you can see down by this main grouping here. So we have our spring-fed streams, indicated by the high connectivity, and also that coarse substrate. So woody debris provides habitat, provides pools, and provides areas where brook trout can go and forage for insects. And that sand provides a really good coarse substrate that allows brook trout to spawn successfully, potentially spawn. And again, going back to the cluster analysis, or the riparian zone, all the streams that had brook trout are found in streams 1 and 2. So we have also, besides just these habitat variables, we're also seeing brook trout found all in streams that are surrounded by hemlocks, or that mixed coniferous zone. So all the brook trout are found in stream 1 and 2. So what are the dynamics of these populations? So these are the length-weight relationships, and essentially we're seeing standard curves here. So as brook trout get longer in length, as brook trout get older, they're starting to basically slow down. So you can see about this exponential growth here. Stream 1, Fulton's condition factor is the K here. So stream 1 had a lower Fulton's condition factor than stream 2. We collected more fish in stream 1 than we did in stream 2. But it also seemed like in stream 1 we had smaller fish. Whereas stream 2, we didn't catch as many fish as we did in stream 1, but we also had higher condition factor, and also we had much larger fish. But again, this Fulton's condition factor is based on a beta of 1, so it's not that these populations are unhealthy, they're just slightly below average, but they are relatively healthy populations for being such small streams. And then this is just a look at the length frequency histograms. And this gives us a potential idea of what the age classifications are. And I separated this out between different seasons because it really gave me a more in-depth look at how these populations are fluctuating between the seasons. So if we look at the spring and summer, so these are primarily surveys that were conducted in late May, early June, we can see that we primarily only have 2 age groups present here. We have potentially age 1 fish around 90 millimeters, and there are age 2 fish potentially around 110 millimeters, maybe some age 3 fish around 150. But when we look at the fall, we're starting to see this age group come into more prevalence here, which is our young of year. which gives me a really good idea that this is an age 1 age group here. So during the late May, early June, these fish just hatched, so we have really low catchabilities of these fish. In the fall time, they're growing they've had time to grow, and we have much higher catchabilities of these fish. So we're starting to see a young of year, age 1, age 2, and then potentially age 3 fish around 150. We see similar ideas here with stream 2, where we have our young of year around 50 or 60 millimeters. And then, like we saw in the last slide, we're also getting much larger fish in stream 2 than stream 1. When we're in the field, we can also see these differences in age classifications as well, where we have our young of year, so very small fish, 50 to 60 millimeters, and these par marks are really prevalent. So these par marks essentially allow younger fish to camouflage into the stream. We see our age 1 fish, much larger than the young of year, and then those par marks are still prevalent. Age 2 fish, we're starting to see much larger fish again, but we see these par marks starting to disappear. And then with age 3, age 4 fish, we're starting to see much larger fish, much larger heads. This is a very predatory fish, and those par marks are virtually disappeared. So pretty much just to wrap up here, when I first came across these streams, I looked at them and I'm like, I can't believe there's brook trout here. It looked like there was very fine sediment, very low in elevation, and it just didn't look like typical brook trout habitat. But once I conducted these surveys and started running these analyses, I really found that these streams had similar findings to other brook trout studies. Once we started getting more in depth into these surveys, where we had coniferous riparian zones, mostly of eastern hemlocks. This primarily could be due to the shallow root structure of the hemlocks. So it's thought that eastern hemlocks have more shallow roots than your deciduous trees, your hardwoods. So they're not tapping into that deeper groundwater. So that deeper groundwater is being able to infiltrate into these streams, causing year-round cool water temperatures, or during the winter time, actually warmer water temperatures. And they also have year-round stream cover, so those needles are constantly, they don't fall off the trees, so there's also decreased light penetration than you would find in hardwood streams as well. And then these brook trout, again, were found in spring-fed streams with high dissolved oxygen, and also have high specific conductivity, which again, that high specific conductivity could be due to these groundwater streams that are found in carbonate rock aquifers, which causing increased minerals, increased conductivity. And then again, as we saw in the PCA, we had an importance of coarse substrates, such as that coarse sand, and also woody debris habitat, which is really important to brook trout of all life cycles. And then this study provides a really good baseline for other projects potentially done within this watershed. I've collected a lot of habitat data, so it could be good for another master's student or another student to basically come in and find other streams that have similar habitats to what I found, other streams in the watershed with maybe that are surrounded by riparian zones of hemlocks, have sand for substrates, coarse sand, a lot of woody debris. So potentially find other brook trout in the watershed. But also it's really good because hemlock woolly adelgid, although it wasn't found in my riparian zones along my streams, it's really close, it's nearby. It's really just a matter of time of when it invades my streams. So hemlock woolly adelgid, this survey provides before data if hemlock woolly adelgid does invade, so we can see the potential impacts on HWA on brook trout before and after invasion. So just to wrap up here, I just want to go through my acknowledgments. My advisor, Andie Graham, has been fantastic in guiding me through this project. My committee members, Dr. Jacqueline Chard in the back, and Dr. Michael Chislock with SUNY Brockport, and also Tom Hoffman with the U.S. Fish and Wildlife. Field assistance provided by a whole bunch of undergraduates, graduate students at Brockport, staff. Would not be able to get this project done without them. And also the property owners for site access. And also I just want to thank the guys out in Region 9 of the DEC. They helped me a lot with getting this presentation started and ready for you folks. So thank you very much, and are there any questions?
So you said that in streams 3 and 4 you didn't find very many fish, or there was none?
We didn't find any brook trout.
Okay.
So we found high diversities of other fish species, and it was interesting because where we found brook trout, that was typically the only species we found.
So do you think it's habitat issue in streams 3 or 4? Because you had talked about aquatic connectivity.
Yeah.
So is there maybe a chance that brook trout just can't get? Because I mean, I'm familiar with the area, and so is it a connection issue, or do you think it's just not suitable habitat?
I think it could be a connection issue. One of the things I did find is that stream temperature, so water temperature did get warmer. So I think that there might be a disconnect between the streams that had brook trout and Black Creek to basically have successful connectivity. But even if they did have connectivity, I think that water temperature would just limit them. Maybe not during the wintertime or the fall, but definitely during the summertime it gets way too warm.
Did you find some of those species that were in creeks 3 and 4 also with the brook trout?
So the streams that had brook trout, we found primarily only mud minnows, which were found in other streams as well. But the streams had like really fine silt pretty much and like really coarse sand. So those mud minnows were prevalent, but they were still found in low abundance. We found one creek chub in stream 1, and that was in an area where we found no brook trout. So it was pretty much solely brook trout that we found. Yep.
I may have missed this, but was there a difference in the watershed, land cover, land use in any of these smaller subunits?
So the streams that had brook trout are primarily found in like a large wetland area, but primarily the entirety of Black Creek is heavily agriculture. A lot of land use, mostly agriculture. I think it was like 70% agriculture. So it didn't really matter where you went or what streams you were surveying. You were probably going to be impacted in some way by agriculture. So, so it was pretty much the same.
But some of them didn't have a silt and some did.
Right. Yep. Yeah, it's mostly the streams that were found that had brook trout had more of the fine sediments like the sand and such. So.
Okay, with that, we've arrived at our break. Thank you, Brad.
Right.